Yes, that's why it's expensive. I can answer your question here. Yeah, here. So ALC, you add a point in the design, and how much do you reduce the estimated variance, obviously, but you can do it with GP, you have an explicit function. So how much do you reduce that? Then you have to integrate over the whole space, and that's expensive. But Bobby tells me that now it's less expensive. He has some tricks. So by using this simple approximation, and you can do better than that, but. Well, that's a very good point. So Andreas Krauss in this MI paper, there was a very nice paper in, I think, JMLR or something, was criticized by the reviewers, as he says, and because he assumed that he knows the hyperparameters of the GPE. And actually, it's a very strong assumption. Who knows? So he did something which was, oh, let me see if it's robust to any, change. And he proved the theorem because he's, very good at that. And okay, fine. But we were not happy with that because we don't want to go for the wrong hyperparameter and then completely, even if it's robust in some way, that doesn't help us. So what we do is we typically estimate the hyperparameters repeatedly. We do MLE repeatedly. But we don't have to do it from the beginning. From the beginning, it's quite, if you have 5 points, really, so you do kind of some guesses, and then you improve that, and you don't do it every iteration. I mean, if we do it, we do it now every iteration, but we learn along the way these hyperparameters as well. So this is again ALM, the maximum variance. ALC, we just talked about it, and this sequential design. Again, this you all talked about this this week. This mutual information or KL divergence. So again, you add a point in the design here. And you take this difference of mutual information. It's a bit funny as a, sorry, it's not readable, but it's how much do you improve the situation in some way with this criterion. You can explicitly put that in this shape, sorry, for GPs, and also each of these can be computed. Obviously, sigma hat is easy. So this is easy to compute. Except where I know you're doing this, maybe because of that picture. So let's say we start with those 2 points, and we say, oh, where is this criterion maximized? Here. And we have a set of candidate points that in a grid. Okay? Then, but let's say we don't have points in a grid. We have we have an additional point next to 1 point in the grid. Suddenly it says, go there, and it's wrong. We had to do something about this. Yes, you're nodding. You experienced that yourself? Yes? So that's it. There you go. So you're ahead of me. So this kind of describes this. I don't want to go into details, but this, let's say, jitter or nugget or information noise, as you describe it. So Joachim worked hard on this to expand about the mean noise in some way. Oh, this didn't compile. I compiled just at breakfast, so sorry. But the nugget is used. Let me not go into the details here, but this is according to the level of noise. What is the predictive variance of the GP? And indeed, this goes to 0 dramatically if you have no noise or very small noise. So you remember this ratio. So we wanted to do something about this ratio, not get the ratio get down to 0. But then if you take 10, let's say you assume a very large noise, then you lose information completely. So 1 was the optimal. Whoop, theorem 1. Whatever. So it's not a theorem, but it's good enough. And if we do that, then suddenly the plot is not here, but we solved that problem. And then we proved that it's optimal. Okay, near optimal. So Andreas Krauss proved that. So we follow his proof. But you're within 63% of the optimal design, which is impossible to find NP complexity. So the optimal design, you're actually using a greedy algorithm such as this one, you actually within 63% of the optimal design, but we cannot prove exactly the same because we have this little approximation, but we are epsilon close to that optimal within 63% of the design for arbitrary epsilon. Sorry. Yes, the theorem is very long. It's not. Yes, you have a candidate exactly. Yeah. The best X. So you have a grid of candidate points. Yeah. Yes. Yeah, you're right. It's combinatorial problem. Yeah, you finite set. Yes, but the finite set represents. I mean, if you have good enough as a candidate set, but you're totally right. Actually, we do practice. In practice, we change. You know, if you're in very high dimensions, it's very stupid a grid. Oh, you understand that. So to explore the space, we actually not only we're adaptive in the sampling, but we're adaptive in the candidate set. So because we may have missed some parts of the space, so we resample Latin hypercubes as candidate sets each iteration. And as a result, let's say if you compare for this simple functions, there are many functions. Yeah, I love this. If I can continue. When you choose a set of candidates, you can enforce some code and minimal distance. Yes. How do you know all this? Because you read my mind. Go ahead. But if you just say, okay, I want to find X that minimizes or maximizes my extent. Yes. Then you can continue to be very close to already evaluated. Yeah, I'm not talking about. Yeah. Yes. Yes, exactly. So we suffer from that. So you know all the details. You know the things that are not in the paper. That's amazing. So for example, we definitely resample Latin hypercubes. We actually draw 1,000 Latin hypercubes per iteration. And we select the few that separates the points the most in some way. We don't want to suffer too much. We can correct. We have this little trick, but we. Yes. No, we didn't care about the covering the space, the input space. But maybe for optimization, yes, we do. It's called the exploitation exploration. Yes. So actually, this is the candidate set. You see, in mice, we pay a price, but just what you said, we pay a little price by resampling to this candidate set. But MLE is the same cost everywhere, but the selection is very heavy for ALC. So you spend time thinking about the next point instead of running your computer model. That's very stupid, right? So as a result, let's say if you compare Latin hypercubes or minimax or here maximin also with so for a number of design points that increases with other techniques, we kind of do better, not always. And we apply that to tsunami model, obviously. The same. Maybe I should just look at the last part where we still do MLE at every iteration to update our hyperparameters, which is the most costly thing to do. When we do every 5, we gain so much more. The ratio here compared to, say, ALC, this is constant. But if we reduce that blue part by a factor of 5, can you see the ratio is much more striking. Anyways, when we do that, that's the total cost, including the computer model run. Obviously, when it's more expensive, the computer model, the more you gain. Or it depends. But, on many aspects of the algorithm itself. Now, we want to use mice in order to improve the surrogate-based optimization. So these people in Paris, Emile Cantal, Nicolas Vaiatis, and others, they have very nice papers. And it's not them introducing this technique. It was done by Srinivas and others in the... This is pure exploration, and UCB means... I never know what it means. Confident... Yeah, uniform. It's not uniform. I don't remember. One day I will remember this fully. Anyways, but these people have used ALM in their sampling scheme. So what you want to maximize a function that's costly. So you want to explore. Let's say ideally you want to build a surrogate and maximize the surrogate in some way. Right? But you can't. But you want to tailor your design to the problem of optimization. So you want to have more points where you think the maximum is, right? So this is this a trade-off between exploring the space and exploiting, that means maximizing where it's supposed to be happening. Since I've very little time, I will just show you this plot. How do we do it? These people have done it before. We just follow their technique. So you have points here. You have a GP that has some uncertainty about it. And the region where you want to sample with mice or ALM, the DDLM, is the region where you feel that the maximum will exist because of this criterion of the region of interest. So the region of interest is this region RT, relevant region, sorry, it's called. So where this F plus, which is this estimate of the maximum, it's written here, sorry. F plus is the mean plus some amount of variance, right? And F minus is the opposite, right? Oops, sorry. So you want this to be greater than a certain value, which is the maximum of the lower bound, F minus. So some idea about, where should I sample for, where should I search for the maximum in that region? And in that region, we apply mice, okay? So what does that mean in terms of, so we're working on the theory now. It's a bit heavy, but in application, so if you look at this function that has, it's a minimization here, but it has actually 3 minima. The minimum is obtained at these 3 places. So it should be quite uncertain, and actually ALM does quite well here. But you see what happens with mice, combining this exploitation with an exploration through mice in this relevant region. We don't spend much time exploring there. You see, we focus on these points that are the locations where the maximum is obtained. So many examples. Another example here. I want to show you this one. This one we do. This is the regret. The regret is this function that I can show you as well. This regret is a very simple function, which is used in machine learning. The value of the true value of the maximum minus the value at the point you are at the moment. That's a simple regret, and then you do cumulative regret as well if you want to. And you can prove results, asymptotic results, using regret. So if I go back to the regret for that particular function here, Michaelis function, actually it should be the other way around, but that doesn't matter. We do much better there. I don't fully understand why we do much better there. And here we do, I mean, why? Because we sample better where it's important. And here it's smooth, so ALM will do fine in some way. When it's smooth, we don't do that well. When it's hectic, then we do better. That's tuning setting. And then last, I'm sure you're not happy with me talking so forever, but this is Cascadia. Again, this region of interest where the really big one will happen. Tsunami and earthquakes. By the way, the earthquake is a big problem because the building codes in that region are not the same as in California. But the tsunami is very important. So the location of interest is here. The quantity of interest is the wave elevation at that location. And now we started doing data assimilation. But what we discussed with Aditya is how do we design the best network? So if you look at Japan, the network is called SNet. It was put in after the great earthquake of 2011. It was put quickly. It's very expensive, about I think $500 million. It's very expensive. Okay, so and to maintain, I saw those buoys, by the way. If each of them is the price of 2 Ferraris, and to maintain them, it's hundreds of thousands. I mean, they're very fragile also. I mean, it's very difficult. Okay, so that's maybe not optimal. You have to do something fast, and I understand the politics behind it, but it's maybe not optimal. And for other countries, really, that are not rich, like Indonesia, Sri Lanka, India, etc. So if I go back to this design, to this question, here for US, US may do it at some point. They have some network that I can show, actually. But it was temporary. I can show you actually, no, I don't show you that, but I can show you data assimilation in action. No, how do I open a GIF? Yeah. So this is the work of Maeda-san in Tokyo. So this is just linear shallow water equation, actually, because non-linear is really near shore, and when you want to do warnings, early warnings, you don't really care about already if it's near shore. So that's, and also it's much faster. So you see, you start with on the left. It's there's no information gathered. It's the truth. And on the right, you start with nothing. You have no idea whatsoever what's going on in terms of, you just assume some basic starting point, and then you learn through this network of buoys, and you see after a while you kind of match the true wave. You match it. So if I go back now to my talk.
But it happens that the tsunami is happening close to your...
Well, yes, it is the case for this illustration, but in practice, let me show you. If I can manage to go back, I don't know. Yeah. And I do, how do I do? Control L. The paper by Aditya in 2016 looked at actually this region, the same region, but for a source that was much higher. It was in this Queen Charlotte Fort. It was called the Hadaguay, to respect the Native Americans.
Your point is to protect the land, right?
Yeah.
If the tsunami happens on the land side of your network,
Yes.
you might not learn much.
No, actually, it's a very good question. Very good question. So if we have buoys on that side, the wave propagates. I can show you a movie if you want, instead of talking. I don't have it here, but it's in my computer. But so the wave propagates actually faster in deep ocean than on shallow water. So actually, you can learn from the buoys that are in the opposite direction about the tsunami, right? The characteristics of the tsunami to infer what will happen on shore. You see what I mean? No?
No, mostly because by the time you learn it, it's already hit the shore.
No. If you are very close to the source, here you can learn in 2-3 minutes.
But it's already too late, so because it's going to hit the shore.
It's 20 minutes here, roughly.
20 minutes.
Yeah. Every minute counts. I totally agree. In Chile, 2010, how close was it in terms of minutes? It's one of the closest. In Japan, do you remember in 2011? How much time? Half an hour, no? No, you don't know. But if we want to build a network, we have to build a network that will be helpful in many situations, whatever the source. So we draw just, Latina hypercube here. We didn't optimize that. We just draw some possible incoming tsunamis. And then we learn. And then we create a set of possible scenarios under which we're going to data assimilate and then select the network that will be optimal for this criterion of best results at the shore for this particular location. Yes, on average over the 50, yeah. Which is not maybe we're still discussing this criterion. On average? The objective function? Yeah. The closest to the truth, which is the truth we know. We know everything because we have drawn these events. So it's a bit what.
You may want to be able to predict
I totally agree. This is discussion for a long time. Arrival time, we will also focus on that because for each of, I totally agree. The network is different for 10 minutes or for 15 minutes, right? Warnings, it's infinite. But actually, Omar, you discussed this design, using design, doing design. So we're trying to do design, but we're trying to design a network which is not what is this object? A network. It's a space. It's a set of locations, right? So if I continue, so what we're doing is this function of the network, as you said, the average of the square differences between the true tsunami and the data assimilated tsunami. And I can show you some first results, but we have not. Yeah, no, you're totally right. For now, we're looking at one value at one location. It's not right. We should do at many locations. We only took the maximum, but we have not even started. To be honest, we have not even started. We're just doing data assimilation right now. What is the right criterion? I don't know. Exactly. What is the objective? But it's a political decision. What do we want to protect against? If it's for every tsunami possible, even the small ones, the network might be different. If it's to protect regions where you have people on the shore and not worry about the regions where you don't have much people, then it's another criterion. It's a very difficult, decision to select these criteria. For us, we were targeting the methodology, and we're still working on it, but we can do surrogate-based optimization of the locations at which you want to build a network. So that's what we do. And we do that, we build a network one by one, sequentially, but it's not sequential design of the network, it's just sequential, or if you want design of the network, but it's not the sequential mice that we're using here. We build a surrogate base of F, which is this function of the network. But we haven't fully started. I haven't had no time for that. Yes? Yes. In the end, yes. It's exactly. This is. You read my mind. You're awake. Indeed, it's where is the next location to put a station at? So if I do that, if I choose one point next to the, if I choose one point here, very close to this gauge, I do data assimilation. I get this. Only with one. Those of you who do data assimilation, I have 2 minutes, 1 minute. Those of you who do data assimilation, it's my last slide actually. This is finished. So but I have responded to some questions. So do you feel that it's right when you have only one location near the location of interest and you do the data assimilation? The data assimilated looks right and then it's completely out of phase. But when you have here, it's the same location, and one far away, which is that dot here. And then suddenly it corrects this phase problem, because you have an idea of the wavelength, maybe of you learn about the phase much more. So it's not true that just I was expecting this to be perfect, saying, well, this algorithm would not work. It will design a network that will be just at the end, put a station next to the location of interest and be done. No, actually it's more interesting than that. And this is just if you use a station far away, you just get this, you get right, maybe the phase is kind of right, but the intensity is totally wrong. So data assimilation is about learning where optimally to distribute information in order to gain information. And I'm done with my talk. Thank you.
Thank you very much.